The next talk is part of the research highlights track of CStore, where we invited papers that have been published in other major systems research conferences. And in this talk, we have Hugo Lefeuvre, I hope it was okay, presenting Unikraft fast specialized unikernels the easy way. This paper also won the Best Paper Award, right, for in Eurosys 2021. So Hugo is a PhD student, and his main research area is in the intersection of systems and security.
Thank you. So hi everyone. I said I'm Hugo Lefeuvre. I'm a PhD student at the University of Manchester, and I'm a core developer of Unikraft. I'm going to present Unikraft, fast specialized unikernels the easy way, a work that we presented last year at Eurosys 21. I'm really happy to be able to present this in person because at the time when this paper got accepted, we only got an online presentation. And so this is the result of a long collaboration between NEC, UPV, okay, it works, the University of Manchester, Lancaster, and Liège. So people in this room are probably relatively well aware of what unikernels are, but just in case I will introduce them quickly. So let's take a look at a VM in the cloud. It could be a web server like nginx on top of Debian. So generally that VM will include an application and a wide range of system utilities, a number of libraries to support that, and a general purpose kernel. Because of the VM abstraction, you have two layers of isolation, the VM and the guest OS's processes. So now a healthy question to ask is, do we really need all of this? And the fact is, probably not. In practice, you'll essentially use your application, a couple of libraries, and potentially a small subset of the kernel features. And you would also only need one layer of isolation since there is only one tenant and application in the VM. So all of these unused blocks tend to bloat the trusted computing base, which from a security point of view is not great, and it also tends to break your performance. So the goal of unikernels is precisely to address these issues that I just mentioned. Unikernels are single application, single purpose appliances. They contain only what you need in terms of user space libraries, kernel facilities, etc. And everything runs in kernel mode. And that's fine because there's only one tenant and only one application in this VM. And finally, components can be specialized to maximize performance. And that's once again possible because there is only one application. So widely recognized benefits of unikernels include really good performance, small image size, very fast boot times, low memory usage, and that allows you to achieve a really high density. So unsurprisingly, there has been quite a lot of unikernel research in the past 10 years. And you might recognize here some of these systems from top systems conferences. So you might ask, is it a solved problem? And why working on Unikraft, yet another unikernel? And the fact is, current unikernels at the time we were working on Unikraft either required significant expert work, which ultimately limits usability, were often non-POSIX compliant, which ultimately limits compatibility, and offered limited specialization potential, which ultimately limits the performance gain that you can get and makes less attractive. So in short, from our perspective, unikernels were not a solved problem, and that's also why we don't see them in production. So that's exactly what we want to address. With Unikraft, our goals are to come up with a design that's at the same time really easy to build and run, that has no app porting or that only requires light application porting, and that offers great specialization and performance potential. So in order to realize this, we conceived Unikraft on the basis of two fundamental design principles. The first one is to have a fully modular kernel, and the second one is to provide high performance specialized APIs. And I will start with the first one. So for those of you who don't know Unikraft, you're probably wondering for 5 minutes why not to go for Linux in the first place. And the answer is that Linux is is not really modular, and that's not going to change anytime soon. So here you can see a graphical representation of interdependencies of components within the Linux kernel. It's really tightly bound, and that's going to limit the specialization potential, the modularity that you can achieve. And note that we would have the same issues with containers, of course. Actually, it would be even worse from a security standpoint because you're sharing the same kernel. So Unikraft instead is built from scratch to be fully modular. So with Unikraft, that figure would look a little bit more like that for Hello World and nginx. Images are really lightweight and really specializable. So now our second principle was to provide high-performance specialized APIs. So let's illustrate this with an example. And let's suppose you have a networked application like Redis. That application will probably interface with the glibc, which itself will interface with a socket implementation on top of a network stack, and finally reaching a high-performance, low-level API. And you can easily think that after having passed all of these steps, there is probably not much left from the high-performance API. So on the other hand, if your application uses UDP, you probably don't care about all these layers and could probably plug at the lowest level directly. And that's quite known. It's kernel bypass. But the whole point here is that Unikraft makes it a first-class OS construct and really easy to use with minimal modifications. So let's take a broader overview of Unikraft. So at the top, you have the application, and that application is going to interface with libc. So, at the moment, in Unikraft, we support newlib and muscle. Under this, you will find a POSIX compatibility layer, and we'll get back to it a little bit later, followed by the kernel. So here, the black boxes that you can see, like VFS Core or UKNetDev, the low-level API, specialized APIs that I mentioned earlier. So to go back to the previous example, you could, if you want high-performance networking, you could interface directly with UKNetDev. And that also applies, of course, to other subsystems that you can see here, such as the file system. For example, you could bypass the virtual file system and plug the specialized file system directly on top of BlockDev. And we'll actually show that at the end of this presentation. And finally, you could also do other specialization stuff easily, like switching the allocator for both the kernel and the application, and even have different instances of the allocator within the same image to perfectly match allocator and components depending on their needs. So to come back to the goals, the first one was to easily build and run VMs. And the best way to illustrate this is probably with a small demo. So to avoid the demo effect, I have a video. So here we're going to use the Craft tool, which is a tool that wraps around Unikraft and simplifies configuration, build, and run of Unikraft images. So here what is going to happen is it's going to fetch the sources, it's going to configure them, it's going to build them, and that's relatively fast. And once it's done, it's going to build, to run the image using KMUKVM. Then we're going to curl it to show that it works. And finish typing, okay, it works. And we can just do it another time and it works. So I suppose it shows that at least for already ported applications, it's very easy to get started and just run it and just try it. So the second goal that we had is to avoid application porting, or at least limit it to the bare minimum. And in the literature, some projects try to tackle this using binary compatibility. And examples of this include Hermetex, or OSV, or Lupin. And that's really nice because you really don't need the source. You can just run it and it just works and you have the benefits. The downside of this is that the system call cost when you do this is still significantly higher than a simple function call, which kind of stands at odds with what we want to achieve in Unikraft. So instead of doing this, we took a different approach. And what we did is auto-porting from source. And what we mean with this is to take the application's native build system and generate standard object files that we then take and link into Unikraft using muscle. And this will work in the vast majority of cases because muscle is actually quite compatible with the glibc. Muscle, of course, will expect Linux underneath, and so it will try to make system calls. And to address this, we have a system call shim layer that interfaces with the actual system call implementations in Unikraft, and themselves sitting on top of the Unikraft kernel. So that was for the principles. In practice, however, when you want to implement a new operating system from scratch and claim Linux compatibility, you need to implement system calls. So how does it look with system calls? So far in Unikraft, we have support or partial support for about 180 system calls. And that is about half of Linux. So you could think, well, it's not much. It's just half of the system calls Linux has. And the thing is, you don't actually need to implement all 350 system calls to have really good compatibility. If you take a look at this 2016 Eurosys paper by Tsai et al., you can see that 180 system calls is roughly equivalent to 80% of application support, considering the Ubuntu distribution. Of course, it matters which of the 180 system calls you implement, like not any of them, and that requires a bit more of a detailed analysis, and we do that in the paper. So to give you a quick understanding of the porting work realized, Unikraft supports a good number of language runtimes, such as Python, and a few frameworks, such as DPDK. So the last point was performance. So let's take a look at a few actual numbers from the paper. And we will first take a look at some results that you would get when using auto-porting to Unikraft, so the method that I described earlier, with this compatibility layer. And let's start by taking a look at image sizes. We measured them for a number of systems and 4 applications. And the results that we can see is that Unikraft ranges between 200 meg and 200K and 200K and 2 megs, and compares quite positively to competing systems. The second thing that we measured is boot times, which is quite important for for the workloads that Unikernels target. And we measured them for a number of virtual machine monitors that you might want to use in different contexts. And we report a breakdown between the time spent in the VMM and the time spent in the guest. So taking a look at QEMU first, it's about 38 milliseconds, which is still quite fast. It goes to 42 milliseconds when you add a NIC. But the really fast boot times, you get them when you start using VMMs that are really thought for these fast boot times. QEMU is not really optimal for that. So when you use QEMU micro VM, you go down to 9 milliseconds, but you can go down to 3 milliseconds using really specialized VMMs like Solo5 or Firecracker. And 3 milliseconds is really fast because it's not very far from the cost of a fork in an exec. So then let's take a look. Yeah, we have, so these boot times are just for Unikraft, but we have a comparison with other systems in the paper. So let's take a look at runtime memory usage then, quite an important metric if you want to achieve really high density on one host. So we measured it for a range of systems, and once again the same 4 applications. And what we can see here is that Unikraft overall keeps its promises ranging from 2 to 7 megs, which is roughly an order of magnitude less than what you would get if you used like a bit of trivial Linux micro VM approach. Finally, let's take a quick look at throughput. So here I am going to show numbers for Redis, but we have more results in the paper that I'm happy to discuss if you have questions. We measured throughput in millions of requests per second for a number of systems, and we recorded them for 2 types of queries. Overall, the virtualized Unikraft is actually quite close to native Linux performance here. So now I presented the kind of results that you would get by using auto-porting from source, but I did not mention specialized APIs at all. So I'm going to spend a few minutes on this. And to illustrate these specialized APIs, I am going to take the example of a specialized file system. So what we want to do here is we want to retrieve a static file as quickly as possible. And so what we did is we coded a Hashtable-based file system that we called SHFS, and that does this perfectly. It's really specialized towards this workload. The baseline is in our measurement is Linux, and we're basically measuring the time it takes in cycles to retrieve a file that exists and one that doesn't exist. So on the Linux side, we get about 2,600 to 4,000 cycles. And it goes down to 2,000 to 3,000 cycles without KPTI because we used a machine that at that time doesn't have hardware mitigations for KPTI. So it might look a little bit different with a very modern machine. So comparing this against our VFS, we get about 1,600 to 2,200 cycles, which is half of Linux, which is already a fairly good benefit given that this is free. Now the most interesting part is probably SHFS, the specialized file system, where by doing this specialization and plugging at these low-level APIs, we can get an order of magnitude better performance. So overall, we think that the goals that we set initially have been achieved. Unikraft is also not just about Eurysys paper, it's actually an active project with a growing community. At the moment, about 200 people. Since its publication, Unikraft was also the basis of multiple research prototypes, in particular in the compartmentalization world, and not only by our group, actually. And you can reach us on GitHub and on unikraft.org. And I also wanted to mention that this is a Linux Foundation project, a Xen project, and we took quite a lot of attention to making this paper reproducible, and all the figures that I presented at the time of the paper. I'm happy to answer questions.
So we have time for questions.
I can do that fine without the...
Okay.
I can hear you.
Yeah. So are there any open source implications like GPL while you are linking into your application?
There is. So Unikraft is BSD. Since the entity that started this project is a company, of course it matters whether GPL or BSD, etc. So we take care of keeping the licensing BSD everywhere. Now, if you take it and do things for yourself, I'm not a lawyer, so I'm not sure what implications it has, but yeah, definitely it has implications. Yeah.
So you had better results with Unikraft than native bare metal Linux for Redis. Is that correct?
Yeah, that is correct.
Can you
Yes.
talk a little bit about that?
Yes. So basically, with the bare metal Linux, you still have the cost of user space to kernel space transitions, right? If you take Redis, that's a kind of workload that does a lot of system calls, like a very high frequency. If I remember, it's about like 20,000 per second or something like that, like really a lot. Well, it's stressing this API a lot. In Unikraft, system call is a function call. So if you're using virtualization with the hardware extensions, it can start to become actually comparable in terms of performance because you don't have the system call cost at all, which means like function call, it's like 4 cycles, and the system call with KPTI 400 cycles. So if you have this high frequency, it's kind of to be expected that you would get close to bare metal.
Thank you.
Yeah.
With respect to security, so have you done any specific work on some specific unikernels to show that they are more protected, more secure? Because now you have some prescribed recipes, and you could do things that are more targeted.
Yeah, so on the security side, I would say that until recently, most of the unikernels that existed were really research prototypes. So they did not necessarily implement basic stuff like ASLR and right-to-RTP protection, etc. Unikraft is actually paying attention to this because it also wants to become at some point something that can be used in production. So I think that it compares quite well on this side. I think the paper just textually mentions that compared to most other prototypes, it implements these basic security features. Now, if we want to go a little bit more state-of-the-art in terms of security, actually that was really the focus of subsequent work that we did, notably on compartmentalization, trying to take this really modular structure that Unikraft has and using it for the benefits of compartmentalization. I don't know if that answered your question. Okay.
So let's thank the speaker once again. Very